All right, this is a video on quadratic functions and transformations, specifically looking at vertex form of quadratic functions. And we'll do an introductory problem and some solved examples as well. So as an introduction, I just want to graph the parent quadratic function, sort of the core, most fundamental parabola, which is y equals x squared. Okay, and so whatever x is, the y value is that x value squared. And so if x is 0, y is 0, x is 1, y is 1, 2 goes to 4, and 3 goes to 9. Okay, so that's what that half of the parabola will look like. Something like that. And then it's going to be symmetric on the left side as well. Those negative numbers, when they're squared, they will become positive values. And so we will have a symmetric shape known as a parabola. That's not a perfect sketch that I made right there. There are a couple wiggles in it, but it gives you a good sense of the shape of the parabola. This point right here is called the vertex of the parabola, the point that's on the axis of symmetry. I consider this the y-axis in this case, but the vertical line going down through the vertex to be the axis of symmetry. And I consider this parabola to be one that I say that it opens up. You can imagine a parabola opening downward as well if it was flipped in the vertical dimension. So that's the parent function y equals x squared. Let's graph some modified forms of this parabola. So first we'll graph y equals 2x squared. So that's going to be a vertically stretched parabola, a parabola that each y value is doubled compared to the y value of the parent function. So if x equals 1, 2 times 1 squared is 2. 2 times 2 squared will be 8. And we will still have a 0, 0 point, and we will have some symmetry on the other side of the y-axis. So compared to our parent parabola, this is a narrower, skinnier, vertically stretched parabola. Alternatively, we can multiply our x squared term by a negative value, which would flip the parabola down, and then also multiply it by a negative 1/2, which would make it a wider parabola. So that is going to look like this. Over 1 down 1/2, over 2 down 2, over 3 instead of down 9, it would be down 4.5, 2, 3, 4.5, and we would have symmetry on the other side of the axis as well. So you can see this parabola looks a little more bowl-shaped here, opening downward. So if I did this sort of in my head, but you can always make a table as well. I'm trying to just talk through what the general changes would be. But we could look at a -3, -2, -1, 0, 1, 2, 3, and we could plug in values for y. Okay, so 0, -1/2 times 0 squared is 0. And then we could simply do the same thing for the other values of x as well. Okay, and those would actually all be negatives because I forgot to multiply by the -1/2. Okay, so that's what those would look like right there. All right, well, another thing we can do is we can start shifting our parabola up, down, and left and right. So let's have this be our green one right here, x squared minus 3. That's the same as our parent function, our parent parabola, only shifted downward by 3. So we would have a vertex at -3 on the y-axis, over 1 up 1, over 2 up 4, over 3 up 9. And then we would have symmetry on the other side of the y-axis as well. And this is what a parent parabola should look like, only shifted down by 3. Okay, so exactly the same shape as our original parabola that we made at the very beginning of this video, only shifted down by 3. We can also shift this parabola to the right and to the left, and this next example shows a parabola shifted to the right by 4. Okay, a common misconception is that subtraction symbol Many times people think it means we're shifting in the negative direction, but we're subtracting, in this case, a positive 4, so we're shifting to the right by 4. So this would be a normal sized and shaped parabola, just with its vertex at 4, 0. Vertex right there, up 1, or over 1 up 1, over 2 up 4, over 3 up 9. And then symmetric on the other side of the y-axis, or of our axis of symmetry, excuse me. Okay, so just to be clear, this dashed line I'm drawing in down through the vertex is the axis of symmetry. Okay, that's a parent parabola shifted to the right by 4. So I want to give you, in general, what vertex form is, and tell you what the different pieces of vertex form mean. Okay, so our vertex will always be at h, k. So this is vertex form that I'm showing you right here. Y equals a times the quantity x minus h squared plus k. And the coordinates h and k are the coordinates of the vertex, the x and y coordinates of that vertex. And I always just abbreviate that with a capital V in front of the ordered pair. Okay, and the A tells us if it's plus, positive, or negative. It tells us if our parabola opens up or down. And if it's large or small, we have a skinny parabola versus a wide parabola. And by large or small, I'm really talking about the absolute value of A. In those cases, the sign of A doesn't matter. I'm just talking about if A is large, greater than 2, 3, 4, or below -2, -3, -4. So farther from 0, we'll have a skinnier parabola. And if the absolute value of A is a small fraction, -0.5, +0.3, etc., we'll have a wide parabola. All right, and so we can make a completely generalized parabola here, and we can tell that the coordinates of the vertex here will be h, k. So the vertex here is at h, k. And we can tell here that A must be greater than 0 because our parabola is opening upwards. And we'll do an example a little ways farther down in this video that'll help us develop the actual equation of a parabola if we're given its graph. Okay, so let's graph a little bit more complex parabola right here. Y equals 2 times the quantity x plus 1 squared minus 3. So right away, we should be able to tell that our vertex is at -1, -3. Okay, and the way I got the -1 is I flipped the sign inside the parentheses. I want you to remember that also you can think of it as x, we're subtracting away the h value, okay, in our vertex form, in our general form. So here, if we have an x plus 1, we're subtracting away a -1. So a vertex is at -1, -3. We can tell this parabola opens upwards. And I want you to think back to our first transformed parabola we did today. This purple one right here, where we were graphing the 2x squared. So here, in this case, A was 2, right? So an upward opening parabola, only the vertex happened to be at 0, 0. In this case, we'll be graphing the exact same parabola, exact same size and shape, only with a shifted vertex. Okay, and just as a way of making this a little more efficient for you to graph rather than simply making a table each time, maybe you can see that we went over 1 and up 2 times 1 squared. We went over 2 and we went up 2 times 2 squared. Okay, so we can do the same thing from that vertex. 2 times 2 squared is 8. We can do the same thing from our modified vertex down here. Okay, so we have our vertex. We can go over 1 and up 2 times 1 squared in both directions. We can go over 2 and go up 2 times 2 squared in both directions. And I'm saying 2 times the value squared simply because of this 2 right here. Okay, it's stretching our parabola up, it's narrowing it in. And then we can sketch our parabola. Okay, So just think about what the modified vertex is doing to our original transformed parabola. If you want to make a table, you're welcome to. I'm not going to do that here. I will just get it set up for you to just remind you what that means. You're always welcome to just plug in points. But that gets to me a little bit tedious and a little bit boring too. So I'd always rather just be thinking about how is that parabola being transformed from the original parent parabola. Our last one we'll do today is just given a graph, try to develop an equation. All right, and so it looks like we have a parabola with 2 clear points on it, and it looks like that is the vertex at 3, 7. So that's going to help us out quite a bit. We also have a point at 9, 4. Okay, so here are the steps to follow. If you know the vertex and if you know one other point, that's the minimum amount of information you would need. You can develop the equation. Here's how to do it. By the way, if you don't know the vertex, you would need a total of 3 points scattered on your parabola to be able to determine its equation. But we can write out our generalized vertex form, and we can simply plug in what we know. This is h and k, and we have a point that's an x and a y. Okay, so let's just plug in all the information. The only thing we don't know is an a. Looks like a should be negative, but we'll be able to determine what a is by solving for it once we plug in some values. So y is a 4, equals our unknown a, x is a 9, and to be clear, I'm using these points over here, which I'm saying are an arbitrary x and y on our parabola somewhere. H is the x-coordinate of the vertex, which is 3, and k is the y-coordinate of the vertex, which is 7. We can just solve for a right now. So we're going to simplify. 9 minus 3 squared is, or 9 minus 3 is 6, and then squared is 36. And then plus 7. We can subtract 7 from both sides. And then lastly, we can divide both sides by 36. And we'll get a fraction, and that's completely okay. We can simplify that fraction to get a negative 1/12. So we have some important information here now. We know the vertex, and we know our a value, and we can write out the equation of our parabola. So our final answer here is going to be y equals negative 1/12 times x minus 3 quantity squared plus 7. To check that work, I would suggest going over to Desmos, plotting it up, and see if you get those 2 same points that we have highlighted on the parabola that you see here. So we got through it, and that's a good place to stop.